Hello and welcome everyone. My name is Dane Menke. I am the Digital Marketing Manager here at REGENESIS and Land Science. Before we get started, I have just a few administrative items to cover. Since we're trying to keep this under an hour, today's presentation will be conducted with the audience audio settings on mute. This will minimize unwanted background noise from the large number of participants joining us today. If the webinar or audio quality degrades, please disconnect and repeat the original login steps to rejoin the webcast. If you have a question, we encourage you to ask it using the question feature located on the webinar panel. We'll collect your questions and do our best to answer them at the end of the presentation. If we don't address your question within the time permitting, we'll make an effort to follow up with you after the webinar. We are recording this webinar, and a link to the recording will be emailed to you once it is available. In order to continue to sponsor events that are of value and worthy of your time, we will be sending out a brief survey following the webinar to get your feedback. Today's presentation will focus on vapor intrusion, specifically with regards to investigating and understanding risk. With that, I'd like to introduce our presenters for today. We are pleased to have with us Dr. Kenneth Tramm, Principal with Modern Geosciences, a Texas-based engineering firm. Dr. Tramm's day-to-day work includes air quality monitoring, environmental due diligence, risk-based closures, and remediation design. Prior to founding Modern Geosciences, he directed environmental due diligence for 2 international engineering firms. He is also the author of Environmental Due Diligence, a Professional Handbook, which provides a comprehensive guide to the due diligence process. We also have with us today Mr. Thomas Szocinski, Director of Vapor Intrusion at Land Science. Mr. Szocinski is a nationally recognized vapor intrusion expert with over 15 years experience as an environmental scientist, focusing on vapor intrusion assessment and mitigation, remediation, site assessment, and brownfield site management. He has served on both state and federal regulatory vapor intrusion review boards, assisting with development of vapor intrusion and mitigation guidance, regulations, and exposure criteria. All right, that concludes our introduction. So now I'll hand things over to Ken to get us started.
Thank you. Thank you very much. Can everybody hear me okay?
Yeah,
that's
we
right.
can hear
You can't answer.
No, I can hear you. It's coming through great.
All right. That's the hard part, just me staring at a computer here. Well, thank you very much, everybody, for tuning in. This is kind of a part 2 of our earlier due diligence focus and screening focus element. So that said, let's jump into the next slide here. So you know who you're at least listening to at the moment. We're a smaller engineering firm, but we focus really in this targeted area that I'm talking about today, specific to environmental due diligence, which can often lead into our vapor intrusion issues, which can lead into our remediation strategies, and then air quality in general, in addition to the ambient stuff that we do. As an overview, and putting these two as bookends together, the first one that we did back in April, and this one we're doing right now, things I wanted to touch on, and I'll touch on both in this, and then emphasize things that we touched on earlier, right? Why are we even talking about it? Obviously, there's a lot of talking about it going on right now, especially if you're in Michigan. How does it fit into due diligence? A little bit of the history part. I won't get into the screening because it's covered heavily in part 1. Please take a look at that if you've not had a chance to yet. And then I want to cover the assessment. So in that term, I'm including the investigation and the understanding of the risk that comes from what you find. So just to set the stage here, right? So why is it a concern? Well, probably most of you listening to me right now are inside a structure. Fantastic if you're not, and my hat's off. But in general, you'll find that most people spend more than 80% of their time indoors. The dynamics of VOCs, when we find them in soil and groundwater and in the soil gas phase, are that they will actually preferentially go into and under those structures that we are in. That, coupled with the risk-based corrective action models that we use, many of them used to determine if we would close a site, may be lacking an evaluation of that pathway. There are some still in place that will selectively not use that as one of the criteria to determine what those regulatory numbers we need to meet are. And then the last part is that those closures will now leave those concentrations in place, and we'll see redevelopment. And long term, we want to understand if we actually have a risk concern or not. So as far as who is asking, well, many of the people listed here below, whether it be a developer, a municipality, an equity partner, probably are going to understand their risk for a site in the form of a phase 1 environmental site assessment. And within the definition of an REC, an EP, and our environmental professionals have been asked to make an opinion on whether a risk is present in the form of a recognized environmental condition, and that can include migration of vapor. So that, to answer the questions for the parties you have below, is probably the first step in someone making that determination. Again, the first part has a lot more elements related to that. The why they're asking, really the long-term risk is a big piece that I have conversations about day to day, such as a company wants to purchase something, we've gotten closure with the state, but I have to put my workers in there. Is there going to be a concern to them or a risk to them going forward? Is there going to be an impact to the asset value? The land itself, the buildings, the investment that they actually put in, are they going to get what they anticipate out of it at the end of the story? Do they want to anticipate the cost to address vapor intrusion in those early business decisions of do we even want to go forward with the redevelopment perhaps? Or just to stay ahead of these changing closure criteria that we see right now, which unfortunately is in some of the headlines today in different states that you're listening to me from, because it's an evolving area. So the science on it will start somewhere and it'll either become less conservative or become more. So that means staying ahead of those regulators or working with, and oftentimes, or knowing that you've been in states where there may be a closure and all the parties have gotten comfortable, but understanding is there a potential for it to be revisited. I won't poke at the guy that's got the TCE litigation. Maybe you guys have looked at that online. All right, we covered last time, and I don't mean to put a zillion words on a slide for you here, but going from left to right, it's good to understand where we are today versus where we have been, so that you understand in the context of if you're doing research on a property that may be closed, does that closure include an understanding of vapor intrusion or not? Obviously, if you're on the right side of this slide, then time period wise, then probably so. On the left side, maybe less so. But if you go back to the 80s and the 90s, we had our early framework to deal with vapor intrusion, whether it was from radon or landfill gas or eventually from VOCs in general. But moving forward, right, we get early adoption of it in 2002 with the draft vapor intrusion guidance, which hung around for a long period of time, and was the original framework that we saw most people moving from and referencing until we finally had some how-tos from the ITRC group. And then we finally had ASTM grabbing hold of these definitions, and then EPA finally putting out some more definitive guidance on what to do and where risk lies and doesn't lie, or at least should be screened in for further evaluation. Out of all these elements, one thing that's going to be important to us, and I'll focus on now, is going to be this little A that you see up there, right, this alpha. So that's for attenuation. So that's going to be our, we see red, you see that little alpha right there, that's for the attenuation factor. It becomes a big part of the story as we move forward. All right, so behind all that work that was done, sorry for the fancy curtains, right, we have what I'll just generally refer to as your conceptual site model, an understanding of what's happening that can lead to why I believe there is, or is not, lines of evidence suggestive of vapor intrusion. The two most significant ones that we often focus on is understanding right at the structure what actually is that soil gas flow rate into the buildings, and then within the structure itself, right, how much air exchange or movement of air are we going to see? Those become the most receptor-based criteria we can look at. The other things are happening in the environment, right? So a release has occurred as you look at the left side. That release is then taken on several phases. It might be in the soil gas phase, it might be free product, it might be a dissolved phase in the groundwater, but each one of those obviously has a volatile component. If we're tracking a volatile organic compound that we have concern will be related to vapor intrusion. So just to jump back to where we were, which is to look at environmental due diligence in general and saying, what are these steps that we normally have that lead us to even beginning the story, understanding the story, and finding an end to our story, right? So whatever we got to first, we actually did our initial investigation. Maybe some site characterization data was collected. Maybe it's ours, maybe it's somebody else's. But we reached a point where we determined we need to screen and say whether there is or is not a concern, right? So one of those early screening efforts for this example you have right here, which is an ITRC example for petroleum vapor intrusion, right? So on our left side, we might screen and arrive at something where you see in the green box, we determine there's an incomplete pathway. There's not enough risk based on conservative criteria for us to say we believe there's a vapor intrusion concern in that structure. And in the middle, we have something that's in between, an area that a lot of consultants spend a lot of time in trying to say, I will now make my investigation to determine if this is true, and I'm actually to the left or to the right. But in this middle spot, right, we're determining that, well, there might be, right? So we've looked at some screening criteria, and we've determined there's a potential for vapor intrusion to exist. I may need some data. And then on the far right, there are situations where you may have enough screening data early to say we need to go ahead and remove the receptors, the people, the sensitive people that we're worried about out of a structure so we can make a determination. Those are the flashy ones that make the headlines and you see in the newspapers. Those are the ones that as consultants we try to help our clients avoid if we do our job correctly. But nonetheless, when we begin in the middle, we might need more data to at least determine the one on the left is correct, we stay in the middle, and hopefully we don't run over to the right side. This is petroleum specifically, and you'll notice I have Mr. Richard Milhouse Nixon over here on the right, probably for two reasons. One, he started the EPA, so we got to give him a little bit of street cred there. But the second is he was fond of investigation, so I keep him around for that. It's hard to do jokes with this stuff here with no audience. All right, whenever you do screening, and so you have this initial criteria, we may do what I showed you on that last slide where you have, I'm in the middle, I've got some data, I think there could be a concern, I think there might not be a concern. When you're evaluating all of those, you have to understand what went into that screening criteria. They almost all, I'll go ahead and say all for these purposes, but exclude if there are preferential pathways in which you would not anticipate attenuation from where the release occurred through some media and then where the receptor may be exposed. So for example, on the right, you see there may be a tank, it's got free product, it's obviously got volatiles related to that free product, and it's got very specific fractured potential pathways leading directly into where a receptor might be, right? So the attenuation happening there is much less than is represented by those models. So you've got to understand the release, the specific guidance in which that was determined, if there are utilities, if there's special lithology understanding needs, or understand groundwater itself. Are you in a place where there's high fluctuation? Your capillary fringe is not measured in centimeters, it's measured in feet. So things such as that may be different than the screening criteria you're going to be using, and so hence you need to see if you need to screen something in more often than you might if it was somewhere else where you understood the conceptual site model. Your understanding of the site said, no, this is either consistent with the model or maybe even more conservative. So we've had one of those two things happen, right? We've done that middle one where we've screened and we've said I needed more data, or we've screened and it would fall out other than there's a preferential pathway of some form or another. So as we begin to look at that and say, what do we need to do next in this due diligence understanding, I'll kind of make a segue of, okay, what did we learn from a lot of these area-wide studies that have been done, and several very high-profile studies. They've had a lot of scrutiny on them, a lot of data collected after the fact. There are some things we can know as we begin to look at what our scope needs to be going forward, right? So some of the lessons learned, if you will. Right, so as I begin to scope, I'm just trying to inform how I would approach a vapor intrusion concern. I've now screened it. I now know I'm going to have to do something about it. So I want to know going in that the inhalation-based criteria that we might use, so the numbers you and I would breathe, those can often be above background numbers, for these specific compounds. It turns out we have lots of compounds around us that would fall under VOCs and even be a potential concern. The second is just to give an honorable mention to TCE, because it's become a big risk driver since 2011 when some toxicological information was updated. The other list of VOCs and related indoor sources, right, where these things could be up to 90% or more of just this compound, right, that may be from your vehicles. So if we've got an attached garage, we have some things that we want to get some information on, all these paints and adhesives, cleaning supplies, gun cleaners, with some of them being just TCE, insecticides, your air fresheners, dry clean clothing. All these things can play into your understanding. So before I back in and I go take a sample, I want to know what I'm going to do with that sample when I get it. So knowing some of this is helpful. All right, what about if we want to get data from other places, right? So we need to be at least informed on the potential for different soil types. Am I dealing with a very coarse soil, or am I dealing with a fine-grained soil that's going to have very tight field conditions, provided that there's not a preferential conduit connected to it? What about moisture? What's the role that it plays going forward, right? So knowing something about that is actually quite helpful. There's more on that in a second. Persistence of different VOCs, right? So in my last presentation, we discussed different types of plumes, petroleum, chlorinated, different types of chlorinated, and average lengths that we could expect in a certain situation. Now, soil gas is different. The soil types will play a big role if something will move or won't move or will be allowed to move, but there's a lot of other pressure gradient issues, specific physical properties of the chemicals we're talking about. Those all play a role into what kind of persistence should I expect. Obviously, the weather conditions themselves play a different role as well. Another take-home from these larger studies that have been done are the communication challenges that come with it. People are less sensitive, in my opinion, to soil impacts that may be all around them, that they just don't have a concern. But the minute you begin talking about things that you breathe, right? We're all essentially fish living in the air that we're in right now, right? We're going to continue to breathe. We don't have a choice. I have a choice if I'm going to drink water that comes out of a well on my property. I have a choice if I'm going to dig a hole in my yard. I don't have a choice if I'm going to breathe. So the communication challenges, you need to know what you're going to walk into when you have that conversation, if you are actually having that discussion with somebody on site, which the second you step in to do this sampling, that discussion might begin. Now, data quality, a lot of labs have really stepped up their game here, but early on, there's a lot of misdetection. I still get some of that where you've got to climb into the actual chemical analysis that was performed at the lab and actually look for some of the clues, maybe the specific ions that were found, the retention times to say, do we really think something was or wasn't there? But the detection limits early on were a big concern. Most of those are known. Again, a lot of states have some very conservative criteria, so you'll want to look at what is my target here? Can I get there? Visit with your lab so you all have an understanding of where you're going. Now, from an indoor air sampling approach, there's two primary approaches to this. One is to have something where you come in and you can screen with a real-time understanding to find those potential interior sources or preferential pathways. There might be an electrical conduit, might be a crack in the floor. That can be done with different tools. Some give you a high resolution, some give you a low resolution. On the flip side, there's taking samples and actually getting an analytical confirmation of what concentrations are physically there. That might be a more passive approach, such as using badges. It might be an active approach with thermal absorption on the end using TO17 for tubes. On the flip side, in the United States, we're more fond of our SUMA canisters, right, an evacuated canister, as you see in the top right, where it's actually under negative pressure and it will pull in air, hopefully a little more foolproof. However, if you don't do all the QA/QC you need to do on that SUMA canister, whether it be the 5-liter one on the left or it be the 1-liter one on the right, you can have some problems. There's a pump to the left of the large SUMA that we would use for moving air in an active tube situation for TO17. Then the sampling approaches you might choose, there are some nuance to knowing if you're going to do a subslab versus soil gas, and even to some extent additional groundwater sampling to help determine understanding the risk at a specific site. In the bottom right, just talking a little bit about specific compounds, an indoor one that we actually do run in actually is in several the reference studies that we use, this E6000, I've never heard of it before, but more and more I go to commercial settings, and it obviously is a very good glue because I keep finding it. And it definitely gives me biased readings when I'm near that. So coming through and clearing out and having an understanding of the environment you're working in is very important. All right, so common errors or things to think about. More specific to your sampling design is the materials you're going to use. You definitely don't want to bias high or low the sample event you're going to be in. Make sure you understand the right location. Am I looking for a shallow soil gas understanding of the site? Or am I looking for deep and shallow? Or am I looking for just deep because I want to be highly conservative? Those are things to discuss with your client up front so they know what the data means to them as well. And as I'll discuss a little bit later on, is some of the attenuation factors might vary based on where you collect that sample and what it means to you. Purging, you don't want to over-purge, but you don't want to under-purge. There's definitely some state-specific guidance to look at first. Then ITRC has some overarching guidance that is generally in agreement at this point. There's been a lot of settling of what's our approach, what's the minimums, what's the expectations, what parameters do we record. Knowing the sample containers needed to get your job done. Knowing how to do a leak check, and by leak check I mean two things. One is to actually confirm the integrity of the container that you're actually going to take your sample in. So if I was doing a SUMA, I need to make sure that I've actually got a SUMA with integrity and it hasn't had a leak and made a problem. So now I've got a vessel to take a sample. Along with that is the sample train, anything above the sample point. I want to make sure I'm actually going to not get intrusion into that. And the third is the sample point subgrade. As I pull any air out, I don't want it replaced or short-circuiting and pulling ambient into it. So on the top right, you see a water dam. That's very common for a subslab point to be our below grade. We can monitor the water and say, are we sucking that in or not? And on the top of that, within this little, I guess just a series of valves, essentially here, we're pulling it and seeing if we actually can hold a vacuum, right? So you need to have some criteria. Again, there's state and federal guidance on what criteria to use for that, so I won't get into the weeds with you, but you can hit me with questions if you want. Knowing the sample flow rate, which from literature, the flow rate's more an emphasis on not exceeding a certain pressure that then would undo some of these precautions you've put in place and can bias your sample result by preferentially pulling from one area versus another. And then understanding your ambient and weather condition impacts, sample container verification. There are some very high profile times when you may want to have individual certifications that your sample container has been cleaned and is free of artifacts. More typically, we'll have batch where they pull one off. We just clean 10. We're going to pull one of the 10, check that one. If that one's clean, we assume the rest of them are, right? So understanding your data needs on that end, there are times when it's all come down to that one sample, and they will buy the whole property if that one sample is clean. Well, you sure want to make sure you know that it's clean. And then your method selection, again, work with your lab, understand your regulatory framework, but your most common ones might be a TO 14, 15, or 17. There are other gases which would be run by different methods, but those are the basics that we generally see. I don't know what that noise means. Again, your comparison criteria is something to keep in mind as you frame out how you're going to do your work. Is it something that's actually in your state? Is it something that's federal? Is it something that all the parties have agreed on outside of that? And then choose your media that you're going to be sampling in. All right, so now this brings us to where we were in this storyline, right? So we were looking at our due diligence before. We've just talked about screening. We pulled it in. We've got an understanding of the framework. So now we really just need a structure. How are we going to investigate if there's a future structure planned or if there's an existing structure planned, right? So some variability with those two that we want to get answers to, right? So we want to understand the regulatory structure that we talked about. Will one event be enough to satisfy all the parties? Will we use some initial screening in the field to actually place our points? They're so important to us, and we have just a certain number we can use. I'll do some initial screening oftentimes and then plan where I put my soil borings and my wells and even my soil gas points. And then do I have all the necessary supplies before I ever mobilize to the field, right? So we have to have that framework. So with that in mind, we want to understand what is our conceptual site model, right, our full understanding of the site. So here's an example of one where we may have a lot of data. I rarely get this level of data. Hopefully my mouse can show up in here. You may have an understanding of what's going on at the surface, right, former structures, current structures, planned structures, soil data, and then some profile understanding of the lithology you're in. Is it going to be fine-grained, coarse-grained? Are there actually known exceedances and releases on the site? Beyond that, where's the groundwater impacted versus not impacted? All these elements will feed into where would I choose to preferentially find a representative sample to help my client make a decision, or to help a regulator make a decision of, do I have the potential I need to go into the structure and answer all those questions, or is there enough information, perhaps subsurface, to answer those questions? They each depend on the site and your conceptual site model and knowing what you want to do next. All right, so with each of these, you'll want to understand the different variability that's ahead of you. So just like that conceptual site model had, right? So if you have spatial variability, so I may actually have a source in one area versus another. I may have heterogeneity versus homogeneity, which allows me to take more samples versus less samples to get the representation I think I need. I want to have an understanding perhaps of the oxygen distribution if I'm dealing with a petroleum VOC. Subsurface buildings and utilities, we talked about preferential pathways before. And then even at the surface, are there pavement or surface water features that may become an impediment that actually can inform why I think things would be in one place versus another. Again, it's all about getting a representative sample that you believe is a conservative understanding of the site. So that's your spatial component. There's always a temporal component too, right? Things change. That's the nature. Groundwater and soil, those don't change as much on us, so we've gotten comfortable. But understanding, am I actually here at a time period where I'm going to collect a conservative representation of the site will be important. Knowing things such as the wind, even the direction and the speed, barometric pressure, the temperature inside versus outside. Obviously, if we're warmer inside, specifically by maybe 10 or more degrees, I feel that's more conservative than the reverse. Precipitation and its ability to actually clog a lot of those pores is an understanding for the site that you're going to want to have. The building itself and how it's laid out and constructed and actually in use will be important. Ambient contaminants that are from indoor and outdoor sources will be very important. And then understanding the potential for sample errors, as we talked about just a minute ago. So here's a basic presentation. This comes from Pennsylvania, where you might choose to take different samples. So in this example here, we've got our concern. In this case, it's a tank. We love to blame the tank, so it's a good storyline to start with. We, in this case, believe there's a preferential pathway. Maybe there's a sewer line that's connecting not only underneath where the tank is, but it goes all the way and to and connects to the home. So in this case, I may have information from what you see as number 1, which is a soil sample, number 2, which is a groundwater sample. There may be a reason to have other groundwater samples closer to the receptor, but beyond that, you can collect samples that are deep soil gas, as you have as number 3, perhaps interior to a utility, or at least the conduit itself, if not the area surrounding the utility, a sample there of soil gas, as I would call it, versus subslab versus interior to the home, right? So laying out and understanding, this is what I want, what's my most pivotal piece of information, what begins to add incremental value. If you're early in the due diligence process, a client probably won't want all that data. So you're going to need to make a decision of what's my most pivotal. Do I want to make, I'm on the left side and I just want to know yes or no, is there a release that's significant enough to be an issue? Do I want to just screen the utility, or do I want to just jump to the end because I believe it is a conservative representation under the right weather conditions, the building operating under normal conditions? So number 6 would give me the result. Or is that going to open a bunch of red herrings and it turns out that glue is hanging out inside, it's going to make a problem, right? So all these just need to be factored in, but at least this is the framework in which we begin to actually collect our data to understand the risk. So now the specifics of collecting each of those samples. So in this scenario, what I have here is if a building is there or not there, we often turn to a soil gas monitor point. It might be called a vapor implant, it might be called a couple different things because the nomenclature is still in play in different regulatory settings. But as you see up here by our friend Richard Nixon, right? So I've got my building outlined here because there may or may not be one, but you could take a sample. It could be near the buildings where it's planned to be, or it could be underneath where the building's planned to be. And so typically this will be some inert tubing that's been selected based on the VOCs you anticipate. And it'll be constructed to a specific depth. Again, that can have a regulatory connotation. I'd say the 5-foot depth has become pretty common, depending on groundwater depth. We do a lot where we have some deeper understanding and some shallow understanding. We develop some attenuation factors for sites, but that's kind of the ballpark way to look at it. You do need to let it equilibrate for a given period of time. That can be hours, depending on how it was installed, to even days. If you're using something with an auger format that turned up a lot of soil, and so we need to let all of that equilibrate. Right, then we would confirm we don't have our leaks either in the probe side, subgrade, or in the sample train side. Then we would collect our soil gas, and usually you construct your end point. On the top right, you have a 6-inch stainless steel, versus on the bottom, I've given you a couple different probe and implant styles that could be used. Again, those are designed based on what you're sampling in and what you're sampling for. All right, now if we do have a building, right, so we have the ability to make some decisions now. I can go into a structure if it exists. I can't go into it if it's not there. So I might use subslab, time-weighted, or come into an existing building and playing with that building to see if we can actually make vapor intrusion occur. Right, so if we've made a decision, we've got a building and we want to do subslab, right? Probably my second most common tool to collect information about vapor intrusion. Why? Because it's pretty inexpensive. Right, minimally invasive. Usually we're going to go through the slab. We'll make a very small opening, relatively cheap because the points are reusable. And then we can do real-time screening either with something as basic as a PID to say hot, not hot, or we can bring a field GCMS out and say it's these specific compounds and within a ballpark these specific concentrations. We can also collect data that would give us some information on is there attenuation happening. For example, is there methane physically there, or is there enough oxygen to attenuate petroleum compounds, for example, on the way up? So that would allow you to investigate and, using these as an initial number of points, and from those make a decision, hey, we should go over here, or it's hot over there. We've done that several times, very effective. It helps our clients get a lot done in one step versus maybe 2 or 3 iterations. And from what I'm told, time is money. Right, so the last part of that is you can then use these points actually to take your sample, similar to before. Make sure you've got integrity of the sample point itself and then the actual sampling train. You can actually get specific information you can here that I can't with my deeper soil gas, which is actually have an understanding of the building pressure differential that may be happening sub-slab versus interior. So there's good information to be had for that. Easy to patch, and we're out. So a good tool to have in your mix. You do need to understand that you can have really high concentrations and there be a lot of attenuation between here and indoor air. So keep that in mind. All right, so if we jump to the other thing I can do when I got a building present, I can take a sample of indoor air. Now I'll go to my last bullet point first here because I've kind of put these in this order, but if I was going to do indoor air and subslab, I would make sure to do my indoor air first, just to avoid the potential that I would bias my indoor air by doing my purging of the subslab. So I'll just mention that because I have these in this order. Within the air, once we step into a building, there's some more sensitivities that happen with being understanding of where you are. Is there a potential for indoor air contaminants to be adding to the story that have nothing to do with perhaps what you're investigating for? So obviously using those same tools we've mentioned before to answer that question is a big step. Screen for those obvious vapor intrusion points. You see down below we've got near an electrical conduit. We do find the electrical conduits which have connections not only through the walls but through the slab. Preferentially we do find a lot more coming from there than we do probably other areas. Understand the weather conditions for where you are, any building parameters if you can get the information on how the HVAC system is working, what it covers, normal operating conditions. Like anything, if you're going to collect a sample for indoor air, you need to know if there's a potential to trigger any of these immediate response criteria, such as the short-term TCE goals that several EPA regions are using, several states have begun to use, because these numbers are low. And I'll talk about background numbers in a second. But then make a decision of how long I'm going to run this, what kind of method am I going to use, and then make sure you've positioned yourself, again, to get a conservative representation of site conditions. The last element that I'll mention with this is with smaller buildings or smaller areas, you can actually go and make a positive and a negative pressure. I was going to say normal, but normal is normal. You're not going to make a normal condition. But you could walk into a facility, investigate it as is, and then walk in and also then control and make it a high pressure building versus a low pressure building. So specifically cause vapor intrusion to happen. So the one you see in the top right, so that was one. If you look at the bottom, under normal operating conditions for TCE, we found ourselves with 1.8 microgram per meter cubed. For PERC PCE, 6.9. When we actually achieved negative pressure in the building, we had 66 versus 148. So we could make a conservative representation of what site conditions were, and definitely could there be a potential for vapor intrusion? The answer would be yes. All right, so background conditions. Now, I've mentioned this a few times, but there's some concentrations of our friends, these benzenes, ethyl benzenes, PCE, vinyl chloride, right? Where if we get into the 95th percentile of expected background concentrations in a residential setting, some of these numbers get higher than some of that criteria I've given you before. Over on the right, you see a description of most commonly found compounds in background studies on the top, going to the least, right? So 96% of the time we're finding toluene. Concentrations 0.03 to 1.9 microgram per meter cubed. And then move on down. Luckily, many of the ones at the top have higher numbers than what these concentrations are found. But as you head to the middle, a few of these are starting to get close to numbers where they would be of concern. And so we really need to know, are we talking about a background setting issue versus an actual release? As we look at indoor air quality, right, we've moved in there. If we've taken a sample, we're now responsible to say, what does that sample mean? So we find ourselves in the middle of this train wreck that exists between EPA and OSHA. So no comedy intended with the accident in the top right, but OSHA, right, so ensures employers provide a safe work environment. They have the authority to promulgate binding national standards to safeguard worker health and safety. Legally defensible, been put into courts and used for decades, and they actually publish permissible exposure levels. Now those do incorporate economic feasibility, right? So I mean, if we're going to judge risk, I can't have that criteria in my understanding if I was just going to be black and white about it. Flip that over, the EPA has generally focused on everything except workplace air. So if you're in those settings where you have a commercial operation, right? So somebody's selling chicken nuggets or burritos, to somebody is selling carpet and tile, right? So we've exited the residential side. Now we've reached this gray area. Now I will say that the EPA in their 2015 Vapor Intrusion Guidance document, right, specifically sets forth that the EPA does not recommend using OSHA PELs. Now within a regulatory context, most states will allow you to use certain PELs or ACGIH numbers or even a few other workplace health and safety based criteria, provided that it's done in a planned setting where there's actually informed employees, and these are the criteria we use. But those happen when there's a dialogue with the regulator. So if I put these into context, right, so here's three I've chosen, right? TCE on the left, tetrachloroethylene or PCE in the middle, and benzene on the right. So on the far left of each of these, I've got their vapor intrusion screening level. My mouse will work for us, right? Of 2.1 for TCE and 8.8 if I was in a commercial setting. My background number is 2. I'm floating right around that. Now this is my 95% UCL, and these numbers you see that I've compared here are based on a cancer risk of 10 to the minus 5 and a hazard index of 1. So not all states, some have lower, some will allow a little bit higher. But either way, these are a good general rule criteria versus if I head to NIOSH and I want to use their criteria, that's 134,000. So that's a far cry from 8.8. Let's check over here at PCE. I've got 180. It's a far cry from the 678,000 from OSHA. or 169,000 microgram per meter cubed from NIOSH. Benzene, studied longer, has probably evolved a little bit as these other compounds will with time, so you'll find these numbers are a little closer, but they're still significantly higher. Now what would be the result if we actually took this and we said, I'm going to move it to somewhere like California, where I may have a 10 to the minus 6 based criteria versus a 10 to the minus 5. So one incidence in a million versus one incidence in 100,000 of a cancer occurrence, and even move my hazard index to 0.1, right? So if we do that, then we suddenly move these criteria for both TCE, for PCE, and benzene much lower, and we start to find numbers that we would anticipate, well, I should find some of those if these background studies are to be believed. So there is some disconnect, and hence my depiction of the train that's kind of gone off the track here. To us, the consultants and the professional community that must judge this, it means we just have to understand where we are, get our own background studies oftentimes to answer this question. So it's just something to keep in mind as you move forward. Now, in all of these, I teach a risk-based corrective action class at the University of Texas here at Arlington, and this is a formula, very basic. It applies to many things, but applies to us here, right? So risk itself, right? Some threshold we are agreeable with. As a community, we made some decisions that we're okay to drive, and a certain number of accidents happen. We allow people to make decisions of what chemicals they want to use in their daily life, and accidents happen from that. So there's a risk criteria, whether that's maybe 1 in 10 to the minus 4 or 1 in 10 to the minus 6 for that cancer rate, for example, right? So risk equals these two things together, the toxicity of the compound that we're talking about and our exposure to it. Obviously, there's radon in the room that you're listening to me in right now, even if you're outside. You're those lucky guys in Hawaii. That said, the toxicity is generally very low because our exposure is low, right? So the toxicity is high if I was right at the compound, if I was down deep enough to be exposed to it, but given enough attenuation from down there to up here, I think we're fine. All right, so I'm going to touch on attenuation just for a second, right? So whether I took groundwater data, soil gas data, or subslab data, there's a way to find yourself some attenuation understanding, right? So what is our attenuation factor? Here's an example where I've taken a soil gas sample at roughly maybe 7.5 feet down at the bottom, and it was 1,000 micrograms per meter cubed. We took an air sample, it was 1.2. Our assumed, I'll call it theoretical, you can call it empirical if you want, attenuation factor for that then brings us to, right, a 0.0012. The smaller that attenuation factor, the greater its impact will be on the samples that we're going to judge. Here's some information. I think I talk too much, even though I'm just talking to myself on a computer. I don't know how interesting I actually am to listen to. If you wanted to say, where can I get my attenuation factor, right, there's a few places. We can do it at a site specifically like I just mentioned. We can do it with radon. That gives you a tracer compound essentially you could work with. You could look at the EPA database. You could use the 2015 default criteria. You could develop your own using models. Either way, you can develop a number. Another thing to keep in mind is the frequency. So here I've given you the New Jersey Department of Environmental Protection criteria, whether I was going to take an air sample, subslab sample, and then the most conservative conditions versus the least conservative conditions. So low on time, I'll let you read those. Now the 2015 attenuation factor, these become the generic ones that almost everybody uses. These obviously are the default for the vessels that we compare to. The groundwater one on the top is 0.001. That's what your vessels are derived from. There's the second one underneath that is 0.0005, right? Lower, more attenuation. So this would be for fine-grained soil, so where I would expect more attenuation to occur, but those are not in your vessels default. When would I expect to have vapor intrusion? Obviously, if I'm closer to the source, I've got the kind of geology that suggests it. I've got moisture content is actually relatively low, and stuff's going to come up and see me. I've got low capability for biodegradation of those compounds, or I've got a building or structure that would lend itself to letting the vapor intrusion come my way. One new one, and I'll call it new, although this is a little bit older now, since it's 2014, is to take a criteria such as regional climate understanding, which is if you're in a certain area, the buildings were built with a certain criteria, and if you put those together, you can develop your own subslab attenuation factor. So for Texas, for example, where I am in, it would be 0.002 under this understanding. So I've put together here, and I don't want to belabor it because I want Tom to speak because he's much a better presenter than I am. But if you look at this, and I'll give you time to do it with the slides that we send out. On the left, right, I've got the compounds. On the top of this, I've got the attenuation factor. If I had a 0.1, what does it mean? 0.03, what does it mean? 0.002, what does it mean? And then I've given you some existing examples that are out there right now, be it a vapor intrusion screening level or if you were in New Jersey with their VOCs. Right, so you can just see the changes that happen. So my inhalation criteria, that's what I can breathe directly. So you're there in green doing it, right? So if it was 11, it was 110 in that default 2002 guidance versus today, if I were to use that area climate base, where's my building at? What's my expected building specific information? It could be as high as 5,500. So there's a lot of different criteria to judge, right? So these are all based on text criteria because that's where I am. There's my little guy. I won't go through this example, but because I think you've got it from the last one. The only other one would be if I was looking to go backwards from groundwater. And so I've got my attenuation factor. This is where you're given the 0.001, which is your default for EPA, versus the 0.005 if you were in clay. I just thought it was helpful to see the differences of what concentrations in milligrams per liter would I anticipate would represent a vapor intrusion condition. So you can see we move from low numbers to a little less low numbers. And you can see how those correlate to a vapor intrusion screening level on the far right as well. So that's the importance of understanding your attenuation factors. Just a note for the petroleum side of this, the EPA criteria specific to petroleum vapor intrusion gives you one other tool that you can use, which is if you can get your data and have an understanding of how deep you are, so depth impacted water, and then the concentrations present, you can use this to derive an attenuation factor. Or, alternately, if you can use the concentration of all your total petroleum hydrocarbons, so add them up, your methane, and then the depth of the soil gas, you can use that to get an attenuation factor as well. So with that, hopefully I've left Tom enough time, and I will turn it over to you, sir. Unless I've put everybody to sleep.
Thanks, Ken. And as he asked, if everybody can hear me, and I'm not going to get a response, but I'm assuming yes. Wanted to get to... Go ahead.
I was just telling you that I could. Sorry.
Great. So I wanted to just take a few moments. For those of you that were on our webinar from last month, I took a little bit of time talking about mitigation. Just wanted to take a few moments to talk about some successful vapor mitigation case studies that Land Science has been involved with. So, and throughout the nation, we've installed and been involved with close to 1,000 mitigation sites. I could hone in on many different states. One of the states that are continuing to show VI concerns and have been hitting the news quite a bit is my actual old hometown of home state of Michigan. So I wanted to take a few moments to talk about a few successful sites in Michigan that Land Science has been involved with, and just kind of walk you through the process of kind of what we've been involved on some of our sites. First one is it's a vapor mitigation site in the Detroit area. It was a national award-winning site, and I'll get into that in a little bit. The environmental firm that was involved with this was AKT Peerless, and it was developed into a medical supply warehouse facility. Basically, what had happened was they took a brownfield opportunity and saw a blighted neighborhood within the city of Detroit, and this is an actual photograph of the neighborhood, and took the opportunity to work with the state of Michigan's DEQ and the US EPA to get brownfield fundings to appropriate the development of this. There was a hodgepodge of contaminants out there, from chlorinateds to mercury to petroleums. It was a old rail yard, commercial settings, as well as manufacturing facilities as well from back in the early 1900s. So with the development and working with the DEQ and US EPA, the environmental consultant was able to determine the appropriate methods of source removal and whatnot, but it still they were still meeting with a vapor intrusion concern before they could do any type of redevelopment. So working with Land Science, they were able to provide a solution with using the Geo-Seal vapor mitigation barrier system with the vapor vent, and ultimately this is the building what you see today if you were to go into Detroit. It's a 275,000 square foot state-of-the-art medical supply warehouse facility. It created almost 200 in-house jobs, but ultimately over almost 1,000 jobs throughout the trucking and in and out transport of the materials itself. Land Science gave the opportunity to give the presentation of a cost-effective and implementation of a vapor mitigation solution for this. For a presumptive remedy, not really, because there was issues out there, but there was no real pointing factor to where these contaminants were because it was just a hit or miss or hodgepodge. So the DEQ did buy off on the opportunity to approve this vapor mitigation system, and the final note I'll have on that barrier was that it actually was able to be approved and funded through the US EPA Brownfield program. This was just the vapor vent layout, so that it was laid out before the actual barrier was to go in, and each one of those loops you'll see there were designed in a passive aspect to then eventually be converted to active if necessary. The Geo-Seal barrier, if some of you were on the previous webinar that we had from last month, I talked in a little more detail of it. I'm not going to spend a ton of time on this, but it's just the 3 layers. You've got your base, which is HDPE. You've got your core material in the middle, and then the top layer, another bond layer, that's HDPE. Bonding that together, and you'll see here in the picture that you actually see the vapor vent laying below that. That's how this system was laid out at the facility in Detroit. This is an actual photograph of the core material, that middle layer, if you will, going down on top of the base layer, and it was under the entire envelope of the building. Here's another picture of you actually see here. If you see these black lines, those are actually where the base layer was seamed together. That's important when you're understanding your barrier systems, to make sure you're creating a seamless effect. And you can see the size of the magnitude of this building. Like I said, it was 275,000 square feet. And then this was just a final picture of the warehouse facility as it stands today. Now, I said it was an award-winning site. To give you a little more information on that, if those who are on the webinar understand the Phoenix Award, if you don't, I'll give you a little background. The opportunity is when you go through the Brownfield Redevelopment and Brownfield Conference, you get nominated or possibly nominated for a Phoenix Award within your region as the top Brownfield project. Well, this facility actually won the Region 5, which is up in the Michigan area, for the Phoenix Award. But then it was ultimately nominated then because it won that award for the grand prize. And this site also won the grand prize Phoenix Award as the top Brownfield project. It also won the People's Choice and a few other awards too. It basically, it's coined as I can say, it swept the awards at the Oscars. The next site I want to talk about is also in Michigan, and this one was a DEQ coordinated site, and it was in Paw Paw, Michigan. For those of you who are not familiar with Michigan's detail, this is like southwest Michigan. Give you a little geological background there. Southeast, southwest are hugely different with the geological formations out there. In this one here, we're dealing with a very shallow groundwater in the sandy aquifer, and it creates a much more prevalent plume distribution through a contaminant site. So first I wanted to talk about the site here itself. You'll see here there's like a groundwater flow that I added into this map for you guys. This is where the groundwater was flowing in a northerly direction, if you will. I did not put the arrow on here, but I had to spin this so you guys could see it. So that's actually in a northerly direction. And then this neighborhood here, as you can see, okay, they're within the groundwater path of where the contaminants happened. So now we had a groundwater contaminant plume going underneath the neighborhood itself. But, okay, fine, what's the distance? As you were talking about earlier today, and you've heard on the previous webinar, that there is a distance of where groundwater is versus where the building influx is. Well, with this being said, this is exactly where the groundwater was on this. It's in direct contact of the basements itself. So subslab depressurization system, it's not an option. Yes, there was a groundwater remediation that was handled through that, and it was actually some of the REGENESIS products that was also used there. But the state of Michigan also realized that there was a vapor intrusion risk at this site because they took indoor air samples or indoor basement samples and identified chlorinated solvents within the basement themselves. So they had to sit there and figure out an appropriate manner to be able to make sure there was a vapor intrusion mitigation and solution for all these residential homes. So what they ultimately ended up moving forward with was using the retrocoat system, and that retrocoat system is literally an epoxy type system that Land Sciences developed that creates a vapor barrier on top of concrete. Here you actually see the sump there, so the sumps were lined as well, and then created a preferential pathway by putting a vent through it as well, so that it could off-gas any venting of VOCs that were collected in that sump through the piping system itself. But the retrocoat was created to create this barrier system across the entire buildings of all those neighborhood homes that I showed you in the previous map. This is just another picture of it as well. Now, before I move on to the next site, I just wanted to talk to you briefly about that the state of Michigan is still working through this site, and they're continuing to collect indoor air samples in the basements of these buildings. And to date, they have not found a chlorinated hit above basically non-detect. And if they were able to determine that it was some other glue that was identified. But there has been no vapor intrusion mitigation, or vapor intrusion from the subsurface into the building since retrocoat has been installed. And the state of Michigan is working with local consultants there to continue to manage these facilities. Next one I want to talk about, and for some of you in Michigan may be familiar with Northville, Michigan. It's outside of Ann Arbor, if you will, for better of a lack of a map to show you, but it's a higher end residential area, neighborhood area, and here's actually what they call the Northville Garage. And in this facility, it actually was a garage. So the actual garage sat right in here, and then up in this left-hand corner, there actually was a dry cleaning facility. So they had the best of both worlds on this. This is, if you go to the state of Michigan's vapor intrusion site, this is recognized as one of their successful brownfield sites. It was the great thing for land science is we were able to provide 3 of our products, Geo-Seal, retrocoat, and a passive vapor vent. Here's actual layer down system again, like I was explaining to you before in the Geo-Seal. So you'll see the actual base layer on the top left, and then you can see the core material on the bottom right. Then the retrocoat itself was as I talked to you guys about before in the previous one, it's a layered system that can be put down on top of concrete. And why was it important on this one for the garage? Well, they had a basement, and for some of you in the Midwest, they often call them Michigan basements, or if you're from Indiana, maybe it's an Indiana basement. But either or, it's the concept that they have a primitive basement there, and they had to be able to seal this basement appropriate because they were going to use it as a walk-in cooler. So we went through the process of designing this system so that the retrocoat could seal these walls and leave to be exposed, and then they could put their cooler system into the basement itself. This is just a quick picture. Up in the top left is the actual basement, the Michigan basement. You can see some of the CMU wall and whatnot. Now the other aspect of the retrocoat was this little half wall you see on the right. So if you ever are in the Northville area, you'll go in the restaurant, you'll actually be able to walk right up to that wall. That wall was just a half wall that had exposed dirt on the other side, and they wanted to leave it exposed. So that wall is why it was recommended to have retrocoat, because the Geo-Seal was going to have a protective coating over it. This one could actually remain exposed to regular traffic. The next site I want to go through it's a residential development in Traverse City. Traverse City is in the northwest up by Petoskey, not too far from the Mackinac Bridge, in Mackinac City and St. Ignace area. It's a higher end. It's actually a lot of folks from the Chicago area come up to the Traverse City area. Big cherry festival, wonderful wines up there too, if I can put a plug for that. But either or, I just wanted to spend some time to talk about this site because it was another combined Geo-Seal and retrocoat with a passive vapor vent, a brownfield redevelopment site that was successful with the state of Michigan. And again, you'll see AKT Piros is another environmental firm that we worked with on this one as well. And they worked through the successful development of a brownfield redevelopment so that we could get this solution. So here I'm just going to show you a quick aerial so you can get some distribution of what we're talking about here. This is where the site sits now. It's a multi-residential development on this Boardman River. And then up here you'll actually see that's where the actual contaminated site, dry cleaner facility, had a chlorinated plume that migrated southeast, sort of, a little bit more east than south, but it moved in that direction towards the Boardman River. So this was the development in the primitive stage of drawing it out, and wanted to hone in on you that there are some benefits of using your exclusionary zones, and we were able to work with the state of Michigan through this to not have to put a barrier system under all these buildings. These left 2 buildings are the ones that actually needed the barrier system itself. And I'll go back here really quick. The ones on the right, the exclusionary zone was determined basically in this zone. It came right in between these buildings. And so once we determined that based off the farthest point, so we had a contaminated groundwater point basically on this corner of the property. Once we determined the distance, we were able to show that the exclusionary zone ended here. So these buildings were determined safe and approved by the state of Michigan not to have a vapor mitigation system. This is actual photograph from an aerial picture just to show you. These are those buildings that I indicated that had the Geo-Seal and retrocoat. And just wanted to put a quick excerpt out there of what we actually got from the Uptown Development Manager. His quote there, without land science, the Geo-Seal and electrical vapor barriers, the redevelopment of downtown Traverse City's brownfield site with this upscale residential townhome would have not been possible. So those were my sites I wanted to spend some time talking with you guys on. I'm running out of time, so I'm going to end it now. But I appreciate your time and everybody joining the webinar, and I'm going to turn it back over to Dane.
All right, thank you very much, Tom. We are out of time, so that will be the end of our webinar. If we did not get to your question, someone will make an effort to follow up with you. If you need immediate assistance with a vapor intrusion solution from Land Science, please visit landsciencetech.com to find your local technical representative, and they will be happy to speak with you. For more information about environmental services from Modern Geosciences, you can visit moderngeosciences.com. Thanks again to Dr. Kenneth Tramm and to Thomas Szocinski, and thanks to everyone who could join us. Have a great day.